Good afternoon and good evening to those of you in Europe, and good morning to those of you awake in Australia. Welcome to Session 3 of the ESIG 2021 Fall Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As I think you know, we are a global membership-based nonprofit organization providing objective technical information, resources, and networking opportunities in support of grid transformation and energy system integration decisions. We do this through workshops, tutorials, webinars, blogs, working groups and task forces for our members, and by producing technical resource material and briefing material for decision makers. Our workshop sessions are all being held online and are open to everyone. This workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Threw of NREL and Julia Matoivasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. You can find us on the web at esig.energy, send an email to info@esig.energy to get our monthly newsletter, and follow our activities on LinkedIn, Facebook, YouTube, and Twitter. ESIG also serves a leadership role in the Global Power System Transformation Consortium, often called GPST, whose mission is to bring together key actors from around the world to catalyze a rapid, clean energy transition at unprecedented scope and scale. ESIG leads Pillar 1 of the GPST, which deals with the research agenda for the system operators. More information on GPST can be found at globalpst.org. In the workshop sessions this month, you'll see the range of issues that need our attention today. If you participate in our working groups and task forces, you'll be working with world-class domain experts on issues that need our attention tomorrow and will be on the agendas of our future workshops. As I mentioned a minute ago, ESIG is a membership-based organization, and this is why your membership and your participation in ESIG are so important. If you are the member point of contact for your organization, please keep an eye out for the annual dues invoice later this month. I thank you if your organization is currently a member and strongly encourage you to consider joining if you're not. Regarding logistics for today, I would ask you to note that the session will be 1 hour and 45 minutes to allow a little more time for presentations and especially for Q&A and discussion at the end. We'll have 4 presentations of 15 or 20 minutes each in the first part of the session, followed by 20 or 25 minutes of discussion and Q&A after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. So you should go to slido.com on your device and enter ESIG14 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also at the bottom of the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we'll address them at the end. We'll follow up with written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG14 as the event code. We would also ask you, if you're comfortable, to identify yourself when you ask a question so we know who we're talking with. Today's session is on hybrid power plants. There's some pretty neat stuff happening around the world on hybrid plant planning, design, operation, and market integration. This session will cover some of the latest thinking and developments from North America. While much of the interest in hybrids is focused on PV battery hybrids, examples of all sorts can be found, including wind battery hybrids, PV wind battery hybrids, and gas turbine battery hybrids, to mention a few. The rate of change taking place in this area is rather dramatic, driven in large part by the battery cost reductions in the last 10 years, but also by the incredible flexibility which these hybrids offer. This is yet another aspect of the changing generation mix and customer preference, which are having a profound impact on all aspects of system planning and market design and operation, all the way from the transmission system to behind the customer meter. Cathleen Murphy, a senior analyst at NREL, a long-standing partner of ESIG, will chair our session today. Caitlin works with a bright bunch of people focusing on how technology innovation, end-use electrification, and energy policies impact the evolution and operation of the U.S. energy system. As a note of interest, Caitlin's undergraduate degree is from my alma mater, MIT, where she graduated in 2007, or 38 years after me. Caitlin, I want to compliment you on your good judgment in school selection. She went on to get her PhD from Caltech in 2012, and her current work deals with understanding the impacts of renewables on the planning and operation of power systems. Caitlin has been an active participant in ESIG for the past few years and brings a valuable perspective and a lot of insight to everything that she does. She's a good friend and colleague, and I'm very happy to have her here chairing the session today. Caitlin, we appreciate your participation, and I'll now turn it over to you.
Thank you, Charlie, and thanks to everyone in the audience for joining us today. We have a great panel lined up, which will bring together a wide range of perspectives on the very timely topic of hybrid energy systems, as Charlie described in his opening remarks. We're going to be hearing from people who study the economics of hybrid systems in both the industry and national laboratory settings, and we're going to consider both the current and future value potential of such systems. We're also very excited to welcome our panelist from Green Mountain Power, who is going to share his perspective on hybrid energy systems as someone who owns and operates hybrid plants in Green Mountain Power. With that, I think we can go ahead and get started. So I will turn it over to our first speaker, who is Derek Stenclik. Derek is the founding partner of Telos Energy, which is an analytics and engineering firm specializing in renewable energy integration and grid modeling. He is currently supporting the ESIG Hybrid Task Force and actively supports developers and utilities in planning and designing hybrid projects across the country. Derek's presentation today will cover motivations for the recent explosion of interest in hybrid energy resources, as well as opportunities for removing barriers to their participation in electricity markets. So Derek, please take it away.
Thank you, Caitlin. Really appreciate it. And thank you everyone else for joining. Looking forward to participating in another ESIG session. Some of you may have been on last week when I was talking about resource adequacy. So in my spare time, I also support ESIG and some work around hybrids, as Caitlin mentioned, also support developers looking to actually put these systems into the ground. So today my focus is going to be more kind of presenting out the work that we're currently doing to support the ESIG task force on hybrids and emerging flexible resources. So this was a task force, you may remember probably this time last year, or maybe it was a spring session, but there was a panel session on hybrids at the last ESIG workshop, and we rolled out that we're going to be doing this task force, diving much deeper into hybrids, why we have them, what are some barriers, what are some really opportunities for hybrids. And so this has been going on from May to October, just about now. We plan on wrapping it up over the next month with a white paper coming out from ESIG and a few fact sheets and deliverables. So we got a group of folks together from across the industry, developers, ISOs, RTOs, utilities, consultants, folks really at the front lines of hybrid technology and hybrid implementation to really pulse them on what is the cutting edge that they're seeing in the industry. So I wanted to go over what we've done thus far, what are some of the key takeaways, and I think with that sets the stage nicely for the rest of the panel session today. A quick recap on what we've done as a task force thus far. We kicked off again in May with a first session really focused on what is a hybrid, trying to get some of the nomenclature consistent in the industry. This is something as a nascent technology or technologies, definitions can be important. And so we spent some time on what a hybrid is, why do we have it, and what are some of the drivers behind that. Second session, one of the big ones, big drivers is transmission and interconnections. We devoted a whole session to that. We recently wrapped up a session on markets and operations. So I'll go over kind of those first three sessions. We hope to have a couple fact sheets out shortly on those. And then the last one, a really important one, is how hybrids participate in resource adequacy constructs and capacity markets. So with all of that, we're hoping by November, early December timeframe to have a white paper out from ESIG that captures the real key lessons and recommendations from that process. So I'll start out with that Hybrids 101 section of what are they, why do we have them, and some of the key findings or recommendations from that. So what is a hybrid? I mean, good to set the stage for the rest of this panel. I think going into this discussion, there's really a lot of question marks. I think, you know, everybody's familiar with the solar plus storage hybrid. I think that's what we're seeing a lot of today. But we wanted to take a look at this from a different perspective or a wider perspective, I'd say. We're accustomed to the solar plus storage hybrid today, but I think there's a huge opportunity for us to get a lot more flexible on what really constitutes a hybrid. Is it just different technologies? Is it different fuel types? What's the role of controls and algorithms in that? What about transmission interconnection and DC versus AC coupling? So we had discussion around all of this, and you can see there's the chart here comes from a DOE report that came out in April around, you know, answering exactly this. What is a hybrid? What are some of the different combinations and configurations? And you can see it covers a wide spectrum of generation technologies at the top, different types of storage and ways to convert energy. It can be either co-located, virtual, or fully integrated. So I think that's a place where there's been a lot of, again, on the definition or nomenclature side, a lot of discrepancy. And so we, being the task force, wanted to sift through that and come up with our own definition. And so, again, this is a group of 25 to 30 folks across the industry, and it spurred more discussion than I was maybe anticipating on what is a hybrid. So I think what we came up with, again, you're never going to get consensus across 24 to 30 people, but where we settled, I think, is on really a hybrid consists of four things. It's two or more resources, and specifically wanted to be very broad in what we said is a resource. So it could be two different technologies, two different fuel types. It could be a generation technology and a storage. It could be generation and load. It could be any combination of those. So again, wanted to be very broad about what a hybrid includes. I think one of the key principles that's coming out of this work is the less prescriptive we can be about what constitutes a hybrid, whether it's, you know, in market rules, interconnection requirements, grid codes, the less prescriptive we can be about that, I think is going to open up a lot of flexibility and a lot of really creative thinking in the industry. So the intent here is to be somewhat vague. I think, again, we don't want to pigeonhole ourselves into what we're seeing today, which is the solar plus battery storage hybrid. We want to think much more broadly about what hybrids could be. Let's get the framework in place today that accounts for that. So again, on that top one, just two or more resources. Second, that we thought was important is really located behind a single point of interconnection. I think this is kind of a differentiator between a virtual power plant, which is made up of resources kind of scattered across the grid. We focused here on hybrids that are at a single location on the grid. And I think that's important because when we start talking about transmission and specifically transmission interconnection, hybrids have a very significant value, which we'll get into in a second. The third is around, you know, these aren't just two discrete resources that happen to be sharing the same field somewhere. This is a coordinated project, a coordinated plant that has some aspect of controls that coordinates the output of these multiple resources. So it's not just the physical location, but these are actually being controlled in a manner that's, if you have solar and storage, controlling the charge, discharge, what's being delivered to the grid, what's being delivered to the battery. There's some amount of controls and algorithms that's making those decisions. It's not just two distinct resources of the same place. And so that really, that coordination piece is important. Ultimately, where I see the difference between a hybrid and just other resources is there may be multiple technologies, there may be multiple resources, but the critical thing is for the system operator, the utility, the ISO, RTO, whoever that off-taker is, or scheduler, they don't really need to see the differences in the different resources behind the meter. They're seeing one coordinated resource that's that's participating in the market or participating with the utility as a unified source. There are a couple of things where, there's a little bit of discrepancy, a lot of discussion. I'd say, the verdict's still somewhat out on the last two. For now, we said it doesn't really require storage, although we're seeing, obviously, most of the attention focused on resources with storage. But again, wanted to open the door for hybridization of wind and solar behind the same point of interconnect or other opportunities there, and certainly load flexibility and things like that. And then lastly, somewhat distinct from co-located resources. So again, getting the nomenclature, the terminology right. I think here we're not necessarily focused on resources that might be just happen to be in the same general area. These are coordinated and controlled resources. So a lot of time on a definition, but I do think, given that this is nascent technology and being actively developed in the industry, I think it's good, again, to, as a first principle, start broad and allow for a vague definition to spur a lot of creativity. So when we start making market rules or grid codes and things like that, let's not be overly prescriptive, and let's let folks have some flexibility in what these resources are. I think a more interesting question is, why are we seeing these hybrid resources? If you look, and Will's coming up shortly, talk about some of the work they're doing at LBNL. They just came out with a great report on looking at the interconnection queues across the country, how much of these assets have, how much of the proposed projects going in are hybrid resources, and it's growing exponentially. You look at places like California, where the vast majority of new solar projects are hybrid resources, certainly because of the amount of solar penetration that they have. But really, we're seeing this trend, that's indisputable, but why? Why are we seeing that trend? And so, again, this group of 24 or so different participants, we came together and everybody ranked what they thought was the most important key drivers for hybridization to the least important. And so that's what you have here, is 1 through 9. And these are really interesting to see it laid out this way. So the first one is fairly obvious, it's just tax incentives. There's the rule that if the battery is being charged from a renewable resource, it can also claim the investment tax credit that the rest of the renewable plant is claiming. So it's very applicable to solar. So essentially, right off the bat, a hybrid resource here, if you're going to build storage, it makes it significantly cheaper to do it out of solar, under a solar configuration as well. So that's probably the first one. But the future of that, we don't know. One, the solar ITC is set to sunset, but also there's talk of a standalone storage ITC potentially in the future. So, if that first one goes away, do we get rid of hybrids altogether? And I don't think so. There's 8 other drivers behind this that are also very important. So the second one, avoided transmission and distribution upgrades. That was a very close second. And so here, having resources, whether it be multiple generation resources or generation and storage, being able to share a single point of interconnect is very beneficial. I think as you start to see these interconnection queues get longer and longer in length, and the transmission spots on the grid is more and more rare to find, I think that's going to be critical. It's how do we use those interconnection points to leverage them to the best extent we can. And you can go down the list. There's reduced development costs because you're doing multiple resources at the same time. Financing, the resource over time has a lot more flexibility if it's a hybrid, and so there's less financing risk. You're also doing multiple projects at the same time. On the solar side, you can capture the DC clipping losses. So if you overbuild the solar panels on the DC side of the inverter, if it's a DC coupled storage, you can capture some of that energy that would have otherwise been curtailed. And then there's some additional ones here. I won't go through each of them one for one, but you can read through that. So again, that is ranked based on a couple dozen folks who have been doing this in the industry for quite some time. I think the important thing, if we're to summarize the what and the why we're seeing hybridization, is what types of hybrids are we seeing? And so today, like I said, this is shared from a presentation Mark Alstrom gave maybe last year at ESIG Forum. But today we're seeing a lot of solar and storage, solar and batteries. But I don't think we should or want to confine ourselves to that type of hybrid. I think that's what we're seeing today. That's what the economics are showing is valuable. It's where there's a lot of development activity. But that's the construct. And then what I think we'll see is everything shares these power electronic conversion capabilities and inverters. And so that's kind of the tool that can interconnect a lot of additional stuff behind it. So you can have additional generation. Basically, if you want to add wind or hydro or basically anything we want behind that, we can continue to be flexible and creative about that. But also different types of storage. So it doesn't have to be a lithium-ion battery. We can have lower cost, longer duration, slower. It doesn't really matter. We can now start to look at different types of storage, different types of load and load flexibility as well. And then, really the key thing here, the key message is let's keep the definition open, make it flexible. So a couple of quick points. I did say interconnection was one of the most, if not the most valuable aspects of a hybrid. And so we just did some real quick back of the envelope math. If you looked at 3 locations in New York, Texas, California, and we played around with different configurations of wind and solar. So here we took an example, again, 100 megawatt point of interconnect, and you had a 100 megawatt wind plant, and you wanted to add 70 megawatts of PV. We did that across 3 different locations, and you can see, you can really bump up. If you look at the capacity factor of a 100 megawatt POI, you can start really cranking up the capacity factors with very little curtailment. So even without storage, you can really leverage that transmission interconnection point. Did the same thing from the solar plus storage perspective. Again, 100 megawatt POI with 150 megawatts of PV and 50 megawatts of storage. Again, almost negligible, no curtailment, and again, can really overbuild the DC side of that and capture some of that clipping and leverage a POI. Now, of course, if you have the land, if you have the transmission capability to have a higher interconnect, you probably do, but I think there's opportunities here, one, to use limited transmission and increase value with the storage, and 2, accelerate the deployment of storage by using existing interconnections. So there's two benefits of doing that type of interconnection. And then lastly, you start combining 3 resources. Again, now 100 megawatts of wind, 100 megawatts of solar, and 40 megawatts of storage. And again, you can really see capacity factors of the plant. Again, we want to think of these hybrids as a plant using that 100 megawatt POI exceeding 60% with very, very little curtailment. So a lot of opportunity there. I won't go in detail. FERC 845 kind of set the stage for using requesting an interconnection capability that's lower than the equipment you have on site. So 100 megawatt POI with 200, 300 megawatts of stuff behind it. FERC 845 allowed for that. The ISO RTOs are going through that implementation. Some are further along, some are less, but that's really what's setting the stage for that, and I think a huge opportunity for hybrids. We also talked about different market participation models, and I want to make sure I give time to the rest of the speakers, so I'll go through these quickly. The important thing here is you have a wide spectrum of, on the left-hand side of this slide, there's the resource, the asset owner self-schedules and makes the decisions on how to use the hybrid. On the far end of the right-hand side of the spectrum is the ISO has kind of full control of the resource and the asset owner doesn't. There's all sorts of differences in between. And I think that's where right now rubber is hitting the road, and exactly who has control of the assets, who controls the state of charge, what are the rules about managing that state of charge and the hybrid resource. I think that's really where this is playing out importantly right now in different market participation models. And so put a few examples here that don't have time to go into just now. There's still a lot of challenges left. We'll have the white paper come out shortly, kind of going through some of these, but basically, again, what do these offer parameters look like in the market? What type of metering is required? What control does the asset owner have versus the ISO and RTO? I think a big one there is there's differences in how the ISO views opportunity cost and what the future might hold versus the asset owner. And we should allow for that difference in opportunity costs, and also on degradation. It's really ultimately how the plant is utilized is going to affect the long-term cost of maintaining and augmenting the storage. And so having, again, asset owners having more say in how these assets are being used, I think is important from that perspective. So something to keep in mind. And then lastly, something to set the stage for the rest of the presentations today is really thinking about revenue streams. And this is a very broad brushstroke of basically some of the work that we've done. And today, I think early storage adoption in general and early hybrid adoption is really chasing after these shallow ancillary service markets. Very lucrative, but somewhat shallow. So if you think of, we've done a lot of work in ERCOT around the responsive reserve service, highly lucrative reserve market, but somewhat shallow. Even ERCOT, which is one of the largest reserve markets in the country at a few thousand megawatts, that's going to saturate very quickly. And so, you know, most places today, and in ERCOT, there is no capacity revenue, but in most places today, ancillary is probably making up the most of the revenue stream for the hybrid configuration, capacity making up most of the difference, very little benefit to that energy arbitrage. I think moving forward, we're going to see a shift. Capacity is going to start taking a larger share of the overall revenue, probably collapsing quite a bit on those shallow ancillary markets. And then really thinking about what are the other revenue streams. And here, I don't think we necessarily know these yet, but ultimately, as we start to see some resources saturate in the market, so hybrids allow for a little bit more flexibility in how deals are structured and how revenue streams. So I think there's a couple of presentations coming up that will go into these in more detail. And with that, I will flip it back over to Caitlin, and we'll probably pause until later if there's any questions, but I'll go into the slide there to see if there's any clarification.
Great. Thank you, Derek. We do have a few questions over on Slido. Audience members, please do feel free to jot your questions down there, and we will return to them at the Q&A session at the end.
Thank you, Caitlin.
All right, next up is Will Gorman. So Will is a researcher in the Electricity Markets and Policy Department at Lawrence Berkeley National Lab. He has led research related to the development of hybrid renewable plus battery projects, and his work focuses on the integration of variable generation into the power system, the economics of distributed energy resources, and the application of energy storage within the grid. Today, Will is going to present his research around whether coupled renewable battery power plants are more valuable than independently sited installations. So Will, please take it away.
Okay, great. So hopefully everyone can hear me. Thank you, Caitlin, for the introduction. And thank you all for joining the panel today on hybrids. Very excited to be here, though I am a little bit biased as much of my research focuses on these topics. And as Caitlin mentioned, today I'll be talking about a recent report that we released probably back in May with the title you see here, Are Coupled Renewable Battery Power Plants More Valuable Than Independently Sited Installations? So this will be the key question and theme of an analytical exercise that we did at the lab to try to evaluate these hybrid projects. But before I begin, you will note my terminology here. You know, we're on a hybrid panel, yet I'm using the word coupling. And this is to be sensitive to the points that I think Derek really laid out quite well on how people are talking about these resources. And so there are definitely aspects of coupling that are contained within hybrids, in the sense of behind a point of interconnection, kind of DC-AC issues, things like that. But we did not evaluate a full co-controlled system, I think, which Derek was alluding to, and I'll go into what we did look at as we go through some of the methods. Okay, great. Let's see if I can get this to move. So just a quick roadmap. I'll introduce and motivate, but I'll go pretty quickly through this because I think Derek covered a lot of this material. And then I will get into the valuation methods. How do we basically value a coupled hybrid system versus a standalone system? Because that will be important to answer that key question. I'll then talk about the results, what we found, and then I'll conclude and transition a little bit to Anna, who will be the next person to talk again about a more modeling-oriented discussion. So you have two analytical modeling researchers talking to you for the next two presentations. So Derek alluded to these graphs. So he talked a lot about the commercial interest, a lot of excitement. Here's just some numbers that maybe many of you have seen. These figures are produced by my colleagues at the lab, Mark Bollinger and Joe Rand. They basically look at roughly 85% of the interconnection queues in the United States, and they see what people are proposing. So you can see the different types of generators on the x-axis, the amount of gigawatts on the y. And the key part for this discussion is the hatched portions of these bars. And those indicate the amount of that resource that is being co-located with storage. So you can see some of those things that Derek mentioned. Solar is by far, at least in the last 3 years, big type of project that is getting co-located with storage, but you do see a smattering of wind plus storage and gas plus storage. It's also interesting to look at the storage section of this bar and see the amount of that is being differentiated between standalone storage and co-located storage. And that decision by developers is going to be at the heart of this analytical work that we did and that I'm going to talk about. Now that was an aggregate US-wide figure on that prior slide, just to give you a little bit of the regional flavor. Derek also mentioned this. So California and the West in general are definitely seeing the majority of these projects and the larger percentages of solar resources co-locating storage. You can see that in the second column here. But there is a proposal for solar plus storage in basically every region we looked at. So it's not that these things aren't being proposed elsewhere. There's just a dominant geographic location where they're being proposed. And then again, thinking about standalone battery versus co-located battery, you can look at that right column to see the percentage of batteries being co-located. So again, there's a regional flair to this, where California, 64% of batteries are being co-located with a VRV or some other generator type, and that is a smaller percentage in some of the other regions that produce that data. And we're really interested in answering the question why. You know, why is this happening? What makes developers choose some of these configurations? And so that's what this slide is meant to do, convey a little bit of that theme. And the title here is a little provocative. And my presentation, what I'm going to talk about today, is not going to be able to answer this question. It's mostly just try to elicit some feelings when thinking about hybrid resources. Because I think historically, you know, when people talked about these decisions, siting decisions, you know, we were thinking about balancing authorities. We'll have, you know, disparate wind and solar technologies, and that those authorities, transmission network, will balance them and optimize them in a pretty geographically dispersed way. But co-location obviously is not doing that, and is intentionally co-locating these things geospatially. Derek went through a number of the reasons why this may be happening, one of them being federal incentives, which might be a big deal. But at the heart of our analytical work in this presentation is going to be, is there potentially an opportunity cost, a real system value opportunity cost that people are leaving on the table when they decide to co-locate versus site storage independently? And we really wanted to try as best as we could to quantify that. Okay, so now how do we do that? What methods are we working with? So it's important to realize that our analysis focuses on historical pricing data, so historical LMPs from nodal markets in the United States, from all 7 nodal markets in the United States. And so we have data from 2012 to 2019. And a nice thing about the coverage that we have looking at all these 7 markets is that these areas are fairly they have a lot of different resource mixes and market characteristics, but they do all operate day ahead in real-time energy markets, so they're somewhat easy to compare. And the central element here, and what's unique and what allows us really to do our analysis, is that in the United States, we use a nodal LMP system which reflects transmission congestion. So there's 50,000 to 60,000 nodes across these markets with a pretty, that allows us to look at system value at a pretty geospatially resolved focus. And that's unique compared to the European counterparts, for instance, who have zonal markets. There are other nodal markets that exist around the world, Mexico, New Zealand, but that is somewhat unique, and it's going to allow us to answer this geospatial question with a little bit more precision than we would have otherwise. Okay, so we have these markets, we have all these prices, so what do we do with them? We basically build a price taker market optimization model. So this is a linear optimization algorithm where we assume that the storage resource or the solar or wind resource do not impact marginal prices. So this is a limitation. It makes it hard to study a future with gigawatts of these things on the system, but it does give us a sense of what the marginal value of building one of these things is on the current nodes. We have 2 algorithms that we deploy. We have an optimistic case, which maximizes real-time energy market revenue with perfect foresight. And then we have a pessimistic case where we develop that optimal schedule with day-ahead prices, but we realize revenue in the real-time energy market. And those day-ahead prices are public by the time of the real-time energy market. So we think of this as a somewhat implementable strategy. So that's the optimization. And we basically put in inputs LMP prices at all of the utility scale solar and wind sites across these markets that we've identified. And then we also select a number of high volatility sites, which I'll describe here in a little bit. And those are our nodes that we focus on. And then we have capacity prices. We do have regulation prices, but we use those in a sensitivity analysis. So I'm not really going to go into those in detail in this presentation, but if you're curious about that, I encourage you to look at the report, which is online. And then we have PV profiles and wind profiles, again, at those same utility scale solar and wind sites, so using weather data from those places. And we output energy, capacity, and regulation revenues. Okay, so now I've discussed a little bit of how we do the valuation. But how do we combine the different values of coupled projects and standalone projects to come up with some metric to evaluate this opportunity cost? And what we came up with in this paper was a coupling penalty. The simple equation is in the bottom, where we take the value of standalone VRE and storage, both in a standalone configuration. We add those together, and we subtract it from a coupled value. And the key aspect here is that in the coupling calculation and the standalone VRE valuation, the VRE components are coming from the same location, same weather data, same node. But when we calculate standalone storage, instead of using that same wind or solar node, we identify the 30th most volatile nodes in each of these markets, and that becomes our high value standalone storage target. I'll describe a little bit later of the metric we use to identify that, but it's a fairly straightforward standard deviation calculation. And so that is really what's at the heart of this coupling penalty, is that there is a geographic option to choose a potentially more valuable node. It's important to point out, and I have this on the slide, that when I show you the results, we do actually consider up to 3 constraints. So the first one I just mentioned is this geographic constraint, where you're maybe missing out on high volatility locations. But we do also model a shared point of interconnection. So Derek was mentioning this a little bit, but there is a chance that you have a smaller point of interconnection than the sum total of the standalone components. So we model that. And then we also have some models on restricting grid charging and seeing how that affects the value of these coupled systems. Now, number 2 and 3 here don't give you any insight into this geospatial question, which is important to us. but they are important constraints to think about when thinking about coupling and hybrid resources. Okay, so let's jump into some results. I'm going to begin with a different metric, so not the coupling penalty that I just described. We'll get to that on the next 2 slides. But I think it's useful to present just what is the value of co-locating a storage resource at a VRE, and that's what we're showing here. We call it the storage value adder. What is the additional value you get from pairing storage with wind or solar? And some interesting trends kind of fall out here. You can see that the value in CAISO begins to diverge from other markets in 2015. You see that prior to 2019, ERCOT in Texas had one of the lowest values for co-locating storage, and that had a dramatic jump in 2019. And comparing those 2 trends, which are somewhat similar between CAISO and ERCOT, are interesting because the drivers are actually different. In California, as many of you know, solar penetration has increased. That has dramatically decreased the value of solar. And so co-locating storage during that trend has been able to boost the value more over time. As solar values has gone down, the storage has become more valuable. In Texas, on the other hand, solar was actually quite valuable in 2019. It was aligned with scarcity pricing events. It just so happened that adding storage when there is scarcity pricing is even more valuable. And so that's what led to that boost. And so it's important that the decision to co-locate and the value you get from it could be coming from different things. Okay, so that's the storage value adder. It's distinct from this coupling penalty, but that coupling penalty, bring that back into your head because that's where we're going next. So this first slide sets the stage where we're going to really look at the storage value at these different nodes we look at. So the top graph shows the correlation between this volatility metric we created, which is just a simple standard deviation, and the resulting storage value at that node. So you can see a pretty strong linear correlation, especially if you look at the different colors. Those are broken up by markets. So some of this spread is just markets that you see here. And so that gave us some pretty good indication that, okay, we can use standard deviation to identify these 30th most volatile nodes in a market. Let's now go down to that bottom chart, and you can compare those high value nodes in black, the storage value that comes at those nodes, to the solar and wind utility scale sites across these markets. And what you can see here is that the median storage value is definitely higher at the higher value nodes, but there's a significant amount of overlap. So it's not a step change, it's not an order of magnitude difference, but there is some money potentially being left on the table by siting storage at a solar or wind node. And so on average, what is that penalty? So what I'm presenting here is kind of the graphical summary of our work. This is where we take the average coupling penalty and we look at it over a few sensitivity cases. So on average, we found that this opportunity cost was $12 a megawatt hour in a default case, but this reduced to a pretty low amount, $1 megawatt hour, when assuming some of these sensitivities. And so I'll step through these and walk down this waterfall basically. So the first is when we allowed the POI to be the sum total of the VRE and the storage system, that reduced this coupling penalty by $1.60. When we allowed the coupled plant to charge from the grid, so giving it that added flexibility to potentially charge when prices are low, that reduced the coupling penalty to $3. I mentioned, we look at the 30 most volatile nodes in these markets. If we use the lowest on that distribution, the lowest of the most volatile, it's a mouthful, confusing, but if we use that lower volatility node, that also reduces the coupling penalty, pretty substantial amount. And then finally, when we use that pessimistic forecasting case, that day ahead schedule, that finally reduces the penalty all the way down to $1. And the key thing to think about, and I think it's the key trade-off that a lot of developers will be thinking through, are evaluating these coupling penalties at their particular location, but then comparing them to a lot of the cost savings, which were the top of the poll results that Derek showed earlier. A lot of cost savings, the ITC, reduced T&D costs, potentially some shared infrastructure or financing costs. And those are important to consider, especially in the context of a coupling penalty. All right, so I think I'm roughly out of time. I want to leave time for Anna and Dan So some high-level, top-level conclusions. We opened by talking about the commercial interest in the interconnection queues. These projects are coming. People are excited about them. In our project, our analytical work, we used historical prices to find that coupled projects could significantly boost VRE value across all markets. So that was that storage value adder, those first results that I showed, showing that storage is valuable at these sites. But we did find that there is a penalty to restricting the location to a wind or solar node, and that can range depending on your sensitivity or how you're thinking about that power plant development. And it really points to how future siting decisions are really going to need to consider nodal volatility deeply when thinking about this storage decision, as well as the cost savings that might come from developing a coupled project. So now I will stop here and we'll turn it over to Anna, who's going to do a more future looking. So I focused on an empirical historical data set. I think Anna will look at something much more into the future, which is definitely a nice complement, I think, to this work. My email is here. Feel free to reach out to me. We'll talk at the end of this as well for questions, and then here are all the names of the team that worked on this with me. It's definitely a group effort, not just me. But I will stop now. Thank you for your attention.
Thank you, Will. Thank you for the presentation and also for inserting a transition for me so that I can just jump right to Anna's introduction and we can keep going. Great. So up next, we have Anna Schleifer, who is a PhD student in mechanical engineering at the University of Texas at Austin. Her PhD research has been performed with the Economics and Forecasting Group at NREL, and it focuses on the performance, costs, and deployment potential of utility-scale solar plus storage technologies. Anna will be presenting her research that explores the future value of PV battery hybrid systems, which really seeks to improve our understanding of which architectures and which configurations might be most appealing to developers and to the grid as we look out into the future. Anna, please take it over.
I forgot to unmute myself before I got rid of that. Okay, thank you, Caitlin. So this is work that I have done with Caitlin at NREL as well as Wesley Cole and Paul Denholm. And so first, I'll just briefly describe our objectives and the methodology we developed, and then I will get into two different parts that show results for PV battery architecture or coupling type, and then the component sizing, so sizing of PV and the sizing of the battery. And so the high level objective is to understand how the value of various PV battery hybrid systems evolve over time in different locations in the United States. And so the first part of this is to look at the coupling type, so whether they're AC coupled or DC coupled, look at the energy and capacity values. And what I mean by that is the reduction in fuel and operations and maintenance costs for the bulk power system. And then the capacity value reflects the avoided cost of natural gas combustion turbine deployment. And then the three locations we look at are Texas, New York, and California. And then for part two, we look at the inverter loading ratio, or the ratio of the DC rating of the PV array to the inverter capacity. And then we look at different battery sizes as well. So the overview of the methodology is, since we were looking at future values, first we use a capacity expansion model to optimize deployment of generation and storage technologies, as well as transmission expansion through 2050. And then we use results from that analysis in a production cost model to get the hourly system operation. And that includes the marginal energy prices and net loads for each location we look at. So we compile those energy prices, we use the net loads to determine hourly capacity prices, and then we combine those with hourly PV generation profiles and a similar price taker model that Will used. So the same limitations apply where the operation of the PV battery hybrids doesn't affect the marginal energy prices. For both parts, for both sections of results, we use read scenarios that assume low cost trajectories of renewable energy technologies, and then moderate cost trajectories for all the other technologies, including battery technologies. In this case, because the energy prices reflect the cost of energy in a production cost model that assumes perfect competition, the revenue maximization from the perspective of the PV battery system is equivalent to the maximization of system value from the perspective of a central operator. So in the first part, we look at architecture. We look at two different architectures, DC coupled on the left here, AC coupled on the right. The DC coupled systems share a single bidirectional inverter, whereas the AC coupled systems have two separate inverters for the PV and the battery. These configurations are from NREL's PV benchmark, which provides costs for different PV battery and PV battery systems. So these are based on, we chose these configurations so we could have costs to compare the values to. The inverter was maintained at 77 megawatts here to keep the ILR at 1.3 for both systems. So again, that's the ratio of the 100 megawatt PV array to the 77 megawatt inverter. So something to note here is that the AC coupled system has a higher total output, so it has 137 megawatts of output. We didn't limit the point of interconnection capacity for the AC coupled system. And then we modeled a variation on the DC coupled system that allows it, or that does not allow it to charge from the grid, so that's a tightly coupled system. And that's for the purpose of comparing or of evaluating the effect of the investment tax credit. So the first part that I'll show here is, remove this. The first part here is to look at dispatch behavior of all of the systems. So up top on the left, you have separate PV and battery systems. So these are operated separately. And unlike Will's analysis, these are all with the same price profile, so same location. And then on the right is the AC coupled system. So you can see in the black line the price signal. And here, because the price signal occurs, or the highest prices, sorry, occur during daylight hours, the AC coupled system operates very similar to, or the exact same as separate systems, where the battery charges overnight and discharges at the same time that the PV is generating to meet those high price hours. If you compare those to DC coupled systems here on the bottom, you can see in the case of the loosely DC coupled system, you're still charging at night, but now your discharge during the day is limited to the shared inverter capacity. So in both DC coupled systems cases, you lose some value because you cannot, or the system cannot provide energy at the full inverter, full PV inverter and battery inverter output. And then in the case of the tightly DC coupled system, even more value is lost because the battery has to charge from the PV array instead of from the grid. And sorry, the negative reflects charging of the battery and the positive reflects anything to the grid. So then as the share of PV generation increases, you can see that higher price hours are pushed outside of daylight hours. So now both the AC coupled and loosely DC coupled system charge later in the morning and discharge in the evening. So now these two systems provide similar value. And then the tightly DC coupled system still loses some value because it has to charge more from the PV during the day. Finally, as the share of PV generation increases even further, you can see that the price profile is depressed during the morning hours because of that PV generation. So that is when the battery charges regardless of coupling type. And then the high price hours are pushed even further into the evening hours. So all of the systems charge during the morning and discharge during the evening. So you can see here that the operations and energy value of all of these systems converge as the share of PV generation on the grid increases. So if we look at capacity value, so just in the top right of note is that for reference, I've included a black line to indicate full capacity credit of a 77 megawatt inverter. And then the lower line is full capacity credit of a 60 megawatt inverter. So the reason I show those reference lines is to compare these standalone systems on the far left. So the pink is the capacity credit of just the battery. The orangish yellow is the capacity credit of just the PV. And then all three coupled systems are shown with the hatched orange and pink. So when PV generation has relatively high capacity credit, then the AC coupled system provides the same amount of capacity value as separate systems. Again, because it can output at the full 137 megawatt capacity during the hours with the highest net loads. The capacity value of the DC coupled systems is limited to that of the shared inverter. So because they share an inverter, the total capacity value of the DC coupled systems is reduced. And then as the share of PV generation increases, the capacity value, the capacity credit of PV by itself goes to 0. And now all three coupled systems have the same capacity value of the battery by itself. And so here you can see that the coupled systems have a capacity credit of 60 megawatts, even though the inverter is at 77 megawatts. So that kind of shows you the mismatch in the design of the configurations we used, because that inverter capacity can't be fully utilized. So when these energy and capacity values are translated into benefit cost ratios, here I have PV by itself in the orangish yellow, battery by itself in the pink, and then the combined value and costs in the black dotted line. So that's basically just the average benefit cost ratio. And the way we calculated benefit cost ratio here is that the benefit is the net energy value, so energy revenue minus energy expense, plus the capacity value, and divided by the annualized cost of capacity. So the capital cost of the system annualized over a 30-year lifetime. So just want to point out real quick here that the large fluctuations in BCR of the PV by itself reflect declining capacity value. So in Texas, leading up to 2030, that dramatic decrease in BCR of PV by itself reflects the declining capacity value. And then the smaller fluctuations reflect changing energy value. And so in general, the BCR of battery components kind of mirrors the BCR of PV. So battery becomes more valuable as PV becomes less valuable. So then we compared the coupled systems BCRs to those of the black dotted lines. So these lines show the change in BCR of a coupled system relative to that black line. So in general, the AC coupled system in green here is a pretty flat line in terms of its change in BCR. And that's because the value of the AC coupled system is the exact same as the value of standalone systems, but at a lower cost because of shared siting, infrastructure, equipment, that kind of thing. The benefit cost ratio of the DC coupled systems starts out lower than the benefit cost ratio of separate systems because of that, because of the limitations in the shared inverter capacity. And so it's not until you see the capacity value of PV by itself decline that you start to get higher benefit cost ratios of the DC coupled systems. And then in California, you can see the effect of the ITC, basically, where it's much higher, especially for the tightly coupled system. And then it declines as the percentage of the ITC declines. So the conclusions from this analysis were that there's not an optimal coupling type across these three areas, especially in the near term. We didn't find synergies in the energy or capacity values, so the value of all the systems was the same as the combined value of separate systems, if not less. And then finally, as the share of PV generation increases, all the coupling types converge toward similar operation and value. And so the caveat with this result is that the DC coupled systems we looked at were not optimally designed. As I mentioned before, the battery was 60 megawatts, the inverter was 77 megawatts. So the next part is to look at DC coupled systems only and look at the effect of component sizing. So for this analysis, we held the inverter rating constant at 100 megawatts. We varied the PV capacity from 140 megawatts to 260 megawatts. So ILR of 1.4 to 2.6, and then 4 different battery sizes. So 25 megawatts to 100 megawatts. And then we kept the duration at 4 hours and allowed the battery to charge from the grid. So in general, as you would expect, increasing the ILR and increasing the battery capacity increases the capacity factor. But there are a couple differences. So for example, in California at low ILRs, when you increase the battery capacity, the capacity factor doesn't necessarily increase. And that's because as you increase battery capacity, more of the PV energy goes to that battery. So you can actually reduce the capacity factor because of battery round trip losses. And then in Texas, you see higher capacity factor increase with higher battery capacities. And that's because we didn't limit cycling in Texas. And so you see that the battery charges at night from wind and it discharges in the morning. And then it charges again during the day. And then when you go to 2030, you see the same trends, except now there's a little bit more curtailment, so capacity factors decrease. So the way that this translates into energy value is pretty similar, or the same trends that you see with capacity factor, basically. So the point of this slide is just to point out that as you go across each row, looking from 2022 to 2050, you see the energy value of PV by itself in yellow there decline, but it declines at a maximum of about 30%, and it still remains higher than the net energy value of the battery. So the point of this is just to show that the battery doesn't necessarily increase energy value unless it does so by capturing clipped energy at higher ILRs to sell later at night. Capacity credit is kind of the opposite. So especially in California, where PV by itself has basically no capacity credit, the battery functions to provide basically all of its capacity credit. And then similar to the first part, that you can't see the label because of my face, but Texas on the bottom row, PV in 2022 has relatively high capacity credit. So that first 25 megawatts of battery capacity gets you to full capacity credit, and then subsequent additions of battery capacity don't improve your capacity credit by very much. So the result of this part 2 is that we think that it's likely in the medium and long term that higher battery capacities will be added to provide a growing share of the capacity value of the system as PV capacity credit declines. And then with these larger batteries, higher ILRs will be enabled so that the battery can capture the clipped energy and shift it to later hours. And I guess the extent of how oversized the PV system will be depends on location. So areas with lower solar insolation like New York can see higher ILRs with less flipped energy. And then it depends on how much module costs decline over time. So basically the competition between the lower PV value and lower PV cost will determine how ILRs increase over time. And we will not be taking questions.
All right. Thank you very much, Anna. As a reminder, please do put your questions onto the Slido website, and we will return to the Q&A once our final speaker has had a chance to present. So for our last speaker, I'm excited to welcome Dan Belarmino. Dan will be changing gears for us a little bit here and talking more about, more from the perspective of someone who designs, owns, and operates hybrid plants. So we've had a lot of our presentations so far been focused on how we think about these plant types, how we model them, how we evaluate and try to figure out what their current and future value might be. Now we're going to turn to Dan to get some insights about projects that have actually been built and deployed on the grid, and some insights of what he's learned as they've kind of revisited what the optimal hybrid configuration is based on their service territory and the value streams that they're going after. I'll also note that this is Dan's first ESIG meeting, so welcome to the community and welcome to this meeting. We're really glad to have you as a panelist. For the quick bio here, Dan Belarmino is the leader of meter operations and former planning and grid innovation engineer at Green Mountain Power. This is the largest electric utility in Vermont focused on providing clean, cost-effective, and reliable power to its customers. Dan has managed Green Mountain Power's grid-scale battery energy storage installation and operation strategy since 2016. And on a personal note, Dan thought that he was going to be able to sneak in this meeting before welcoming a new member of his family, but actually was surprised to welcome his son late last week. So just really want to thank Dan so much for taking the time during what I'm sure is a very tiring and exhausting period to put together these slides and to talk to us today. So Dan, thank you very much for being here, and I'll turn it over to you.
Thank you, Caitlin, and thank you all for having me here today. Yeah, the past week has been very exciting and amazing, but also very exhausting. So if I fumble in my presentation, I'm sure you all would understand. So my presentation is about GMP's perspective in terms of owning and operating hybrid or co-located solar and battery storage systems. I will quickly touch on our design considerations, the use cases and operation strategies to maximize the value of energy storage, and explain how we quantify the benefits, and finally comparing the operation and economic benefits of DC coupled versus AC coupled solar and battery sites based on how we operated these systems. There you go. Little intro about Green Mountain Power. Green Mountain Power, or GMP, is a small electric utility in the state of Vermont. We serve approximately 265,000 residential and business customers. Our focus is to find new ways of doing business to meet the needs of our customers with integrated energy services that help people use less energy and save money while continuing to generate clean, cost-effective, and reliable power in Vermont. We're also proud that we are a B Corp certified company, meeting rigorous social, environmental, accountability, and transparency standards, and committing to use a business as a force of good. So I'm going to talk about a little bit about energy transformation, which kind of drive a lot of our solar and battery installations in Vermont. Vermont, like every other state, is in the midst of transformation in how we produce, transmit, store, and consume energy. We are shifting from that traditional one-way traditional grid system to a more dynamic, relying on both the supply side and customer load management. GMP has a plan for leading this transformation in a way that delivers dramatic grid cost savings for Vermont as we move as we move to a home, business, and community-based system, if we leave, let the industry continue its trend, it will continue to drive the costs, drive up the cost for customers if we do not manage them. And also, our GMP based on our what our customer wants, we have an energy vision of 100% renewable of our portfolio by 2030. I'm going to touch a little bit about the solar installation in GMP. We also have a goal in Vermont that to have 10% of our energy use comes from local renewable generation by 2032. To hit that goal, Vermont will rely mostly on solar. The reason being solar is cheaper, easier to deploy, something that realistically we can do in Vermont, and the only appropriate resource we can do in scale. Ideal wind sites in Vermont are on top of the mountains and ridges, which is challenging in terms of installation and public support. And also, we have maximized the potential for hydro sites in our state. Unfortunately, we can't just rely on solar for our portfolio. So, so here comes the energy storage, and we feel that energy storage has provide a very important function that is not available to other energy resources, which is its flexibility. Our key now is the key here is how to stack several value streams, such as peak reduction, energy arbitrage, or any ancillary services to maximize its value. We see energy storage, especially battery, will play a critical role in reducing our peak costs, obligations, as well as improving local power quality, resiliency, and provide revenue for our customers to drive down the cost. More importantly, we see battery storage to help address issues of the day, but because of its flexibility, it will help, we can adapt as needed to help address the evolving needs and market conditions in the future. Today, the way we use the energy storage is mainly for peak reduction, for capacity market, or we call it the ISO peak, and regional network services. Those, if we reduce our peak obligation, kind of reduces our cost. And also we use the energy storage for ancillary services, mainly for frequency regulation market as an added revenue stream, while our battery is not used for peak reduction. The value for us, at least for Green Mountain Power, of co-located solar and battery sites, as Derek pointed out in his slides, is mainly cost savings. Number one would be the income tax credit, ITC, that kind of lowers the cost, the overall cost of the system. In our research, there's really not a lot of kind of guidance on how we can obtain the ITC. So we feel that if we have a co-located or hybrid system, that kind of guarantees us that we meet the criteria. Another reason for us, the big value for co-located system is to reduce the interconnection costs, such as communications like fiber protections, line upgrades. Those are big cost drivers to distributed energy resource projects. And a lot of those big costs really kind of like prevents from like scaling up or having more DER installation in our system. We also find that having a co-located solar and battery sites can easily provide grid resiliency, distribution islanding, which I'll touch a little bit. And today we're more focusing on that in terms of finding location that will help our community for grid resiliency, to help with future for long outages. Here's a list of our solar and battery sites, co-located solar battery sites. Our first one was our Stafford Hill project. It was a DC coupled project configuration. Stafford was our first, first co-located battery site. With the idea of is to take advantage of the solar clipping. It was originally procured in 2013, commissioned in 2015. Where the batteries back then were its infant state. So we had a couple different battery technologies here. The lithium-ion batteries is for fast response for frequency regulation, and we use lead-acid batteries for long duration output. As we learned after a few years of operating Stafford Hill, and kind of the battery manufacturers become more like having more lithium ion become more like a better technology, we realized that AC coupled system is much better based on our needs today or the markets we participate in. The main disadvantage we learned from DC coupled system is their curtailed or limited performance during peak reduction or time that it spends in the regulation market, which the next slides, my next slides will show and compare our operation between DC coupled systems versus the AC coupled system. We also learned while operating Stafford Hill that we need at least 4-hour battery energy capacity to meet our peak reduction needs. Then the next project we developed was the Panton project. Based on the lessons learned from Stafford, we used this project. We learned that we don't want to do DC coupled system. We just use AC coupled system, and we use this project as our standard for future projects in terms of configuration and operation. We also use this site to test and stack several value streams, both market and grid benefits, and how to prioritize our operation. And finally, the most recent ones commissioned in 2019 are the 3 solar battery projects, which were similarly configured to our Panton project, but with larger battery capacity. And this time, we are attempting or in the process of attempting to capture the ITC to further lower the overall cost of the system. So in these slides, I'm going to compare, just show the high level operation of the battery in a year, how many percent in a year that the battery operates in a certain way. Here, the Panton site, AC coupled system, 7% of the time, or about 25 to 30 times a year, we operate the battery to reduce our, for peak reduction, to hit the Ford capacity peak and regional network services. And then about 4 times, we use that 4 times a month in June, July, August. That's the time that we hit the FCM peak. And we also operate the battery about 1 to 2 times a month on other months for regional network services. When the battery is not participating in the reg market, we put this system in the frequency regulation market. So as you can see, basically 91% of the time, or about 333 days, the battery operates in the reg market. And then for the other, it's basically the batteries either idling, in maintenance, or charging to get it to appropriate levels of state of charge before the peak event or before going back to the reg market as the state of charge decreases due to losses. On the right is the snapshot of Stafford Hill operation. Because it's DC coupled, we use the batteries to charge from solar during the solar hours, and we just discharge to maybe about 40 to 50% of its state of charge during the evening peak hours before we put the batteries in the reg market at night for about 8 hours per day. Any charge left after participating in the reg market, we usually discharge in the morning peak hours, and then charges from solar again during the day where the cycle continues. And for our 3 new projects that have operated in similar projects that we similar to Panton, but now kind of we consider the ITC. We have a goal to hit 85% of solar charging. Again, the ITC is another way for us to stack the value stream to lower the overall cost of the system. We to operate this, to make sure that we hit the 85% goal of solar charging, we had a little bit of trial and error to make sure we hit this target. At first, we did just cycling the batteries, charging from solar during the day and discharging at night. And then we realized that we're not really getting the full value of the batteries based on that operation. So we start participating in the reg market with bias signal, which is we use a charge signal only during the day and discharge only at night. So it's a 2 megawatt system. So the battery would operate at 0 to +2, discharging at night, and -2 charging, 0 to -2 during the day. Then over time, we learned that we can participate in the reg market with neutral signal during the day as well when the solar is producing, and we can still hit 85% of our solar charging. And that's kind of where this graph shows here that 56% of the time we are either idling or doing solar charging, and 38% of the time we're in the regulation market, while 7% of the time we're trying to hit the peak. We do not have a system that DC coupled system that we participate in ITC, but I think inherently they do. Just based on our operation, I kind of come up with this graph based on the dispatch strategy that we've used for AC coupled battery with ITC. This one I want to show you what the peak reduction performance of Stafford Hill. This was in 2016. I kind of want to show you what the how it performed, where it got curtailed. As you remember, Stafford Hill is a 2 megawatt battery system, the output capacity. But during this time, during the peak hours, the battery output is curtailed at 1.1 megawatts due, or possible 2 megawatts due to solar. This is actually an example of actual example of Anna's presentation earlier, stating the loss of value of DC coupled system, since it can't use the full output capacity of both the battery and the solar systems. It should be noted though, this is like our ending 1600 or 3 to 4 p.m. for the peak, that the peak hours now that we're seeing is pushing later in the day. It's actually an hour ending 18 or from 5 to 6 p.m. In the summertime. So in theory, the loss of potential peak reduction by the battery would be lower as the peak is pushed later in the day as the solar output wanes, but also the solar output wanes later in the day as well. So a little bit of show you the calculation, how we calculate the savings. We estimate the FCM peak reduction saving is based on the auction price, reserve margin, and assumed transmission losses. For each megawatt of FCM peak reduction from like 2019 to 2021, the calculated savings is roughly 100,000 per year. It's a little over 100,000 per year, but also note that the auction price for the following years is going down. So I think 100,000 would be a good number to just for the purpose of comparison of what is the loss value of DC coupled versus AC coupled. So as I noted earlier, Stafford Hill at 2 megawatt output capacity, the maximum savings, if it was, it can use its full output capacity, the battery output capacity in 3 years is about 600,000. But as noted earlier, since it's limited based on the solar output in the last 3 years, we see that we estimate that about $160,000 is lost value because it's curtailed or limited by the solar. It's the same scenario for frequency regulation market, what we've seen. So for patent site, no ITC constraints. The performance in the frequency regulation market, the total revenue that we got in 2019 and 2020 is just over $400,000. And PEN, like I said earlier, PEN participating in the frequency regulation in the reg market when it's not not used for peak reduction. So 91% of the time it's in the reg market. Using PEN's revenue as a baseline, if Stafford participated in the regulation market in 2019, 2020, I should note that we're no longer participating in Stafford in the reg market because the battery, like I said, the battery, it was the infant stage. Right now, it's no longer able to participate in the reg market. But if we calculate its maximum calculated reg market revenue, it'd be approximately 150,000. So we lose about 250,000 or more on revenue on a DC coupled system, based on our experience. Again, our experience in the operating in Stafford and what we've seen in curtailment and kind of lost revenue. We quickly realized that DC coupled system is not a good fit for our needs today, and possibly in the future because of its lack of flexibility. Another thing I'd like to share is our distribution islanding project. So in Panton right now, we are kind of trying to get the value stream of grid benefits. We focus more on resiliency. We have a distribution islanding project that is ongoing. We are currently in our commissioning stage, actually. So the island system will consist about 51 residential and commercial customers. The island boundary, which will include the town hall, the town garage that could serve as an emergency shelter for the town of Panton residents. And the island also includes a cell tower to keep communication in case of long duration outage in the area. Depending on the state of charge and when the outage occurs, either at night or during the day, in theory, or high chance that the battery in the solar system can support the load in the island boundary indefinitely. Again, we use this as one of our main criteria right now to find solar and battery sites in our system, in our area. We find communities that could benefit from resiliency. We learned that from like 8 years ago from hurricanes that kind of isolated some towns and they were out of power for like a week or two. And we see this as a great value for customers in the area, for our community. And at the same time, we can capture the value streams in market benefits. And when it needed, it can provide resiliency for our customers. So the takeaway, the main takeaway, solar and batteries are key to grid transformation and GMP's and energy vision. Co-located solar and battery storage sites provide significant installation cost savings, again, lower the cost for our customers, and also provides grid resiliency opportunities for our community. AC coupled sites are preferred over DC coupled sites due to operational flexibility. As I noted, results in higher peak reduction savings and higher regulation market revenue. That's my presentation, and thank you, and I turn it to Caitlin.
All right, thank you very much, Dan, and thank you to all of the panelists for the great presentations. For our panelists, please do turn on your videos for the Q&A session, which we will switch to now. Audience members, please do go over to slido.com and either insert your questions or you can also vote for the existing questions so that we make sure that we're touching on the ones that the majority of audience members are most interested in hearing verbal responses to during the call today. I'm going to give the audience a minute or two to do that while I kick us off with just one question. That way I can read through the questions sort of in the ranked order after people have had a chance to vote on those. So my question is really looking across all of the presentations today and trying to understand sort of what we know and what we don't know. So the interconnection queue data, I think, shows a huge amount of enthusiasm for hybrids, especially in certain markets. Eric has teed up some of the potential motivations for those, and we're capturing some of those motivations both in our analysis and also in the presentation that Dan just gave. But there seems to be a little bit of a disconnect still. The enthusiasm, I would say, is really clear, and the explanations for it, at least in the modeling and the data that Dan presented, it's a little mixed. You know, there are benefits perhaps, but it's not as clear cut as, yes, hybrids are going to take over the world based on the valuation analysis that we've done and the data that we're looking at for hybrids. So I just want to invite the panelists to offer their perspective on what might help explain that disconnect. Clearly, our models don't capture all the potential values. Dan was just talking about resiliency value, for example, which none of us are looking at in our models. But are there other aspects that we're just not capturing or not fully grasping when we try to look at what could explain this huge industry interest in hybrid systems? That's for all of you. Anyone who wants to come in?
Caitlin, I'll maybe jump in first. One thing we have to be careful about with the interconnection queue data, it really shows the exuberance or the excitement. You know, first of all, not all those projects will go forward, but I think more importantly is, and we've worked with many developers firsthand on some of those projects, and oftentimes people will submit a hybrid option into the interconnection queue because it's easier to get it in there and put it in the queue, and they are saying, well, now I have the option to deploy storage if I want to, but I'm not necessarily planning on it. And so, you know, depending on where you are in that queue position and how far along you are, you can always change that. So some people are putting it in there with, one, the project may never come to fruition at all, and then two, they can always take out the storage component oftentimes.
I have an opinion on this, so I guess I'll just jump in. You know, I think one of the challenges, especially from the modeling perspective, is it seems like a lot of the benefits to hybrids are on the cost side. And so like my presentation was all value side. I think we do some more work at the lab that is trying to do a cost benefit analysis, and obviously Anna's is more of a cost benefit analysis framework. But you know, we don't really have great data on that cost side. We qualitatively know that there's T&D savings, that there is some shared infrastructure savings, and there's some great work at NREL that tries to do this from a bottom-up perspective. But you know, anecdotally, conversations I've had with developers who've looked at my work, they're like, yeah, I mean, your cost benefits are probably on the low end of modeling. And I mean, I can't anecdotally cite, you know, it's hard for me to model that. It's just this kind of hearsay in some sense. But I think there really could be a big cost story here that we just don't have data for, and that's a missing element that I think would be great if people, you know, want to share it or people are going to start collecting it. But it's also missing because a lot of these projects haven't been built, so it's sometimes hard to do the real counterfactual analysis of like, well, what would it have been had I developed this in a separate, and so that's just a hard modeling question, but I think a pretty important one, especially given Derek's poll responses, which was like cost. So.
Great. Anna, Dan, anything you'd like to add?
Yeah, so in the utility perspective, definitely it starts with a cost. We're a regulated company, and a lot of the first thing that we look at is, does it provide value to our customers? Does it provide, you know, make sense to invest in this system? And now the first thing the regulators look at is the cost of the system, and we try to kind of maximize its value based on operation, the market participations that we participate in, and that kind of covers the cost a little bit over time. And one of the issues that actually we're having trouble is, for instance, in grid resiliency, we put a lot of focus on it, but it's hard to quantify the cost savings. And right now, our grid resiliency projects are more for demonstration, and the new ones that we're putting in are more, like community-based. So we're trying to kind of work with our communities to provide some funding and GMP to support, and mainly because we can't, it's hard to quantify the benefits of it and to compare that and put that in the additional cost of putting such system and capability.
Thank you. Anna, anything you want to add before we switch to the audience questions?
Yeah, I definitely agree with the cost side of everything that people have said. The other part is that my analysis was focused on system value. And so from the perspective of the grid, it doesn't matter if your battery and your PV are co-located. From the perspective of a developer, there's a level of control over revenue that the battery provides. So that could play a large role in kind of mitigating risk that your PV system by itself will decline in value.
Great. So what I'm hearing from all these responses is that maybe this gap that I thought there was, we have to move up a little bit one of them and move the other one down, since not all these projects will be built as hybrid, and there's a few different value streams or value potentials that we're not really capturing very well, including this cost savings potential. Okay, so we'll switch over to the audience Q&A now. My plan is just I'll march through the list based on kind of the audience ranked order. And anything we don't get to verbally, we will send written responses to after the webinar. So our first question is from Mark Alstrom. But Will, this is for you. High volatility implies congested transmission locations where interconnecting as a generator is very expensive. Are you mixing storage as generation versus transmission values?
Yeah, so this is, I think this is a great question. And it's probably one that will warrant a longer discussion than we're going to have here, especially because we want to get to other questions. But so I think that's right. I think it is true that storage has transmission value. Storage is transmission and energy shifting value if you're thinking on the gen side with coupling it with VRE. But I think, from my perspective, when I think of locational margin prices, I think of those as the prices that generators get paid, or at least someone who's taking on that off-taking risk if they're getting paid at some aggregated node. And so, it's not a transmission value in the sense of there's this ERCOT-CREZ line that's going to get built or not built based on storage. Like, that's not what we're studying here. We're studying a locational marginal price, which is the energy price and congested price that a generator would get paid at that location. But I think more broadly, your point raises this notion that, look, Will, you've set up this decision of like, should I co-locate or should I develop these at a standalone location? And I was like, oh, there's this coupling penalty, there's this opportunity cost. But that's only really an issue if a developer is saying, I can either co-locate or I can develop standalone. They could be saying, well, no, I'm going to do both. And so then they can take advantage of, and we see that, right? We see standalone batteries and we see coupled batteries. And so I think that is a caveat to my analysis, our analysis. I think the opportunity, in the world in which you're deciding one or the other, I think there is still that opportunity cost. You could, if you can only build one battery and you have this choice, should I put it in a transmission constrained area or should I put it in a wind or solar site? And I think that choice is real and there's an opportunity cost to that choice, but it might be a false choice if developers are that much more holistic in their battery program. So that's one response.
Great, thank you. Derek, this next question is for you. This is from Ian. I did not see deployment acceleration as value in your slides. Expanding generation at an existing facility allows us to boost deployment quickly. Is this seen as a potential source of value for hybrid systems?
The short answer is yes. That is, I think, a really important driver in this. So should certainly be in the list. I think I was kind of including that in my number 2 around avoided T&D upgrades. So not only is it you avoid the upgrades, but you avoid the queue process potentially, which is, sometimes the time of the interconnection queue is much more costly than the actual upgrade cost. That being said, I personally need to do a little bit more homework on which ISOs and RTOs allow for overbuilding on existing points of interconnect without going through the full queue cycle. I know, for example, MISO has what they call surplus capacity, where you can add storage to an existing interconnect, and you still obviously have to go through some study work to get the models and everything verified by MISO, but you miss the full class year interconnection queue cycle. So I still have a little bit of homework on which ISOs allow for that, which ones don't. If you know, you could send that my way, that'd be great. But yes, I think the accelerated deployment could be a huge benefit to both the system. So anything we can do as system operators to accelerate that and allow for that is good. And then for the developers, I think it's a huge opportunity, especially for folks that have a lot of assets already out in the field.
Great. Okay, I'm going to jump down to a question for Anna, which is, what was the most optimal battery to PV megawatt ratio when using DC coupling? And did you evaluate what megawatt hour capacity for storage duration was optimal? And because I kind of know what your answer will be, maybe you can share with us some of your insights about the trends and the directions that you see and where we might start to see kind of some inability to capture the full value potential based on either we can't recover all of the PV generation, or maybe the storage doesn't have any more incremental value to it.
We didn't find an optimal ILR, for example. That depends on location. So in New York, we saw ILRs up to 2.2 or 2.4 with minimal clipping, whereas in Texas, you get up to around 2 and you have a good bit of clipping. And so the level of clipping that you're willing to accept depends on the cost of that additional PV capacity. So the incremental addition of PV capacity is going to cause some wasted energy, and so that cost-benefit analysis just depends. In general, the battery should be sized to kind of fill in for capacity credit. So if you have a 100 megawatt inverter or an interconnection capacity, for example, and your PV provides only about 25 megawatts of capacity credit, it makes sense to add 75 megawatts of battery. That changes very rapidly, especially in Texas. As you saw, like between now and 2030, the capacity credit of PV can decline pretty rapidly. So the battery capacity basically depends on PV capacity credit. We did see that we step back. Curtailment increases no matter what. And with 4-hour storage, you cannot eliminate curtailment totally in the Reed's scenario that we used. No matter how well, if you have an ILR of 1.4 and a 4-hour battery at 100 megawatts, you're still not going to eliminate curtailment entirely. So I know that's not very satisfying, but it depends.
Great, thank you. Dan, 2 quicker questions for you, hopefully. First, you showed frequency regulation revenue numbers for your plants. The question is, was this revenue annual revenue that you were showing?
So the one that I showed there is for plant and site, and that's a combined revenue for 2019 and 2020.
Great. And another question for you, Dan. This is a little bit open-ended, but when does it make sense economically to invest in co-locating batteries, especially if you're not considering ancillary services markets? So are there conditions when the cost savings there are really worthwhile, and what are they?
So it really depends on kind of like your goal in terms of what you want to do. Like I said earlier, for instance, grid resiliency, how do you put a value on that? Unfortunately, we work in an environment where cost and revenue and and value streams is very important, and it has to be quantified, and we have to show that in the next 20 years and how that investment pans out. So right now, without any ancillary services or market participation, we don't see a lot of value for energy storage installation. There are some areas that have transmission congestion. We've had looked at it, but we haven't really kind of penciled in so far. We don't see it as a best option at the moment.
Great. Okay, well, that brings us to the end of our webinar for today. Excuse me. I'd just like to thank our panelists for their great contributions and discussion today, and thank all of you for your participation. This has really been an excellent discussion on the evolving thinking on hybrid power plants and the outlook for the future. As a reminder, we will follow up with written answers to the questions that we didn't get to during the Q&A. I'd also like to remind you that the workshop sessions are being held on Tuesdays and Thursdays throughout the rest of October. We have a session next Tuesday on rate alignment and demand participation, which will be chaired by Ahmad Faruqi of Brattle. There is no charge for the sessions, and you are all invited to attend. Further information can be found on the ESIG website. So thank you again to our panelists and participants, and we look forward to seeing you again on Tuesday. Have a good rest of your